Right now, tonight, light is landing on your eyes that has been traveling since before the Earth existed. Some of the faint points in the night sky are so far away that the light reaching you left its source over 1 billion years ago, back when the most complex life on this planet was still just simple, single-celled organisms drifting in shallow oceans. That light has been in transit non-stop for over 1 billion years. Here's the question I want you to sit with before we go any further. In all that time, all that traveling, all those years crossing the emptiness between here and there, how much has that light actually aged? Take a real guess. 1 billion years, obviously? Some fraction of that? Drop your answer in the comments, because I promise you the actual answer, the one backed by some of the most well-tested physics we have, is going to surprise you. And it's going to force you to rethink something you've probably never questioned before. What a photon, the actual particle of light, really even is. If you're the kind of person who wants an answer this counterintuitive explained properly, not just stated and moved past, go ahead and subscribe, because that's exactly what tonight's video is going to do. Think about what an ordinary journey actually involves for a second before we get into the physics. A hiker crossing a mountain range experiences every single step of that crossing. Every sunrise, every ache in their legs, every mile of accumulated distance behind them. A spacecraft crossing the solar system experiences every single day of its multi-year voyage. Its onboard systems ticking forward, its instruments aging, its components slowly wearing down exactly the way any machine does over years of operation. Even something as simple as a letter traveling through the mail or a package shipped across an ocean exists continuously the entire time it's in transit, sitting in trucks, warehouses, and cargo holds, its material slowly weathering, however slightly, with each passing day of the journey, the ink perhaps fading a fraction, the paper perhaps yellowing almost imperceptibly, small. Ordinary evidence that time has in fact been passing for that object the entire time it was making its way toward its destination. Every single kind of journey we've ever had direct intuitive experience with involves this same basic feature. Distance covered and time elapsed march forward together, hand in hand inseparably. You cannot cross a great distance without a proportional amount of time passing for whatever's doing the crossing. That's not really a law of physics we consciously learned. It's baked so deeply into how we experience the world that it barely registers as an assumption at all. It just feels like what traveling means. Here's the assumption almost everyone carries around without ever examining it. We think of light as a kind of traveler. Something that sets out from a star, crosses an unimaginable distance, and eventually arrives here, at your eye, or at a telescope's lens, having made a journey the same way anything else makes a journey, existing continuously through every single moment of that trip. The way a hiker exists continuously through every step of a long trail. Under that assumption, it feels obvious that something crossing 1 billion light years of space must have aged 1 billion years along the way. The same way a hiker walking for a year has undeniably lived through that entire year. That assumption feels so basic it barely seems worth stating. And it's wrong, in a way that doesn't just tweak the picture slightly, but overturns it completely, once you actually follow the physics all the way through instead of stopping at the comfortable, intuitive picture. It's worth being honest, too, about why this particular assumption is so hard to shake, even once you've heard the correct answer stated outright. Every single physical intuition we've ever built, from childhood onward comes from experiences at ordinary, everyday speeds. Speeds so far below the speed of light that the strange effects of relativity are completely, totally invisible in daily life. Our brains simply never had a reason to develop good intuitions about what happens at the extreme edge of possible speeds, because nothing in the environment we evolved in ever moved anywhere close to fast enough for it to matter. Expecting our gut instincts to correctly handle light-speed physics is a bit like expecting someone who has only ever walked to correctly predict what happens to an object moving at orbital velocity. The tools our intuition uses just weren't built for that regime at all. To understand why, we need to start somewhere that might seem unrelated at first, not with light's age, but with what light actually is, physically, at the deepest level modern physics can currently describe. A photon is the name physicists give to a single quantum, a single discrete packet of electromagnetic energy. Every time you see light, from the sun, from a lamp, from the glow of a screen, you're detecting enormous numbers of these individual photons arriving and interacting with your eye. Each one carries a specific, precise amount of energy determined by its frequency, how rapidly its associated wave oscillates, following a relationship discovered in the earliest years of quantum physics. The energy of a photon equals a fixed constant of nature, called Planck's constant, multiplied by that frequency. This relationship, worked out by Max Planck around the turn of the 20th century and later used by Einstein himself to explain a puzzling phenomenon called the photoelectric effect. Work that eventually earned Einstein his Nobel Prize was one of the very first cracks in classical physics that led directly to the entire field of quantum mechanics. The photoelectric effect itself is a wonderfully concrete little puzzle worth understanding, because it's the exact observation that forced physicists to take the idea of light quanta seriously in the first place. Shine light on certain metals, and electrons get knocked loose from the metal's surface, but only if the light's frequency is high enough, regardless of how bright or dim that light is. Dimmer light of a sufficiently high frequency knocks electrons loose immediately, while even extraordinarily bright light of too low a frequency knocks nothing loose at all, no matter how long you leave it shining. That result made no sense under the classical picture of light as a continuous wave, where brightness alone should have determined whether enough energy eventually built up to free an electron. It made perfect sense the moment you accepted that light arrives in discrete packets, each one carrying an amount of energy fixed by its frequency alone, with brightness simply controlling how many of these packets arrive per second, not how much energy any single one of them carries. Before this discovery, physicists had assumed energy could be transferred in any amount at all, smoothly and continuously, the way you can pour exactly as much water as you like from a jug. Planck and Einstein's work showed that light, at least, doesn't work that way. It comes in discrete, indivisible packets, quanta, and you can't have half a photon any more than you can have half of a single indivisible unit of anything. Higher frequency light, like the blue and violet end of the visible spectrum or ultraviolet light beyond what your eyes can detect, carries more energy per photon. Lower frequency light, like red light or infrared beyond what you can see, carries less energy per photon. But the photons themselves are, in a very real sense, identical in kind, just differing in this one specific quantity. Here's where things start getting genuinely strange, though. and its strangeness that's been experimentally confirmed so many times in so many different ways that it's no longer really in question, even though it still defies ordinary intuition every single time you actually sit with it. A photon has no rest mass. Physicists have measured this to extraordinary precision. Using a whole range of independent methods, everything from carefully analyzing the behavior of magnetic fields across enormous astronomical distances to precision laboratory experiments designed specifically to detect the tiniest possible deviation from zero. And every single test has come back consistent, with the photon's mass being exactly zero, though to be fully precise and honest about it. What experiments actually establish is an extremely tight upper limit on how large the photon's mass could possibly be. A number so close to zero that for every practical and theoretical purpose, physicists treat it as exactly zero. Since no experiment has ever found even the faintest hint that it's anything other than that. It's worth appreciating just how seriously physicists take this specific question. Precisely because so much of modern physics quietly depends on the photon's mass genuinely being zero. Maxwell's equations, the foundational 19th century description of electricity and magnetism that still underlies our understanding of light today, only work out cleanly in their familiar, elegant form if the photon truly has zero mass. Give the photon even a tiny non-zero mass, and electromagnetic forces would behave subtly differently at very long distances than they currently appear to, something physicists have looked for carefully, using measurements of planetary magnetic fields stretching across enormous distances, without finding a single hint of the kind of deviation a massive photon would produce. If it turned out, decades from now, that some future experiment finally detected a tiny but definitely non-zero photon mass, it wouldn't just be an interesting footnote. It would force a meaningful revision of some of the deepest, most successful theories in all of physics, which is exactly why physicists keep testing this specific question again and again with increasingly sensitive instruments rather than treating it as settled and moving on. Having zero rest mass changes everything about how a photon behaves, because of a specific deep connection built into the structure of Einstein's special relativity between an object's mass and the speed it's allowed to travel at. Objects with mass, anything with even the tiniest sliver of it, can never reach the speed of light, no matter how much energy you pour into accelerating them. Because the amount of energy required to push a massive object closer and closer to light speed grows without any limit, approaching infinity as your speed approaches light speed, meaning you'd need an infinite amount of energy to actually cross that final threshold. You can actually see this play out directly in real particle accelerators, machines built specifically to push particles as close to light speed as engineering allows. The Large Hadron Collider, the largest and most powerful particle accelerator ever built, buried in a circular tunnel spanning 17 miles beneath the border of France and Switzerland, can accelerate protons to something like 99.9999991% of the speed of light, using an enormous amount of energy generated by thousands of superconducting magnets cooled to temperatures colder than deep space to get that close. And yet, no matter how much additional energy engineers pour in, that speed keeps creeping only microscopically closer to the actual speed of light, never quite reaching it, exactly as the equations predict. Engineers and physicists running these experiments aren't fighting against some solvable technical limitation, the way you might fight against friction or air resistance with a sufficiently clever design. They're fighting against a fundamental mathematical boundary built into the structure of the universe itself. one that no conceivable amount of future engineering could ever push past for anything carrying mass. The closer you get, the more energy each additional tiny increase in speed demands, an asymptote the universe simply won't let you cross if you're carrying any mass at all. But something with exactly zero rest mass isn't bound by that same restriction. In fact, according to the equations of special relativity, a massless particle isn't just allowed to travel at the speed of light. It's required to. There's no other speed a truly massless particle moving through empty space is physically permitted to travel at. Light doesn't casually happen to move at the speed we call the speed of light. Being massless and moving at that exact speed are, mathematically, one and the same fact, two ways of describing the identical underlying physics. This is worth pausing on because it's such a different picture from how we intuitively think about speed and motion. We tend to think of speed as a choice, or at least a variable, something an object can have more or less of depending on circumstances. How hard something was thrown, how much fuel a rocket burns, how strong the wind is. For a photon, speed isn't a variable at all. It's a direct, unavoidable consequence of what the photon fundamentally is. Ask a photon to slow down, even slightly, in a genuine vacuum, and you're not asking it to do something difficult. You're asking it to stop being the thing it is entirely, since a massless particle moving at anything other than light speed isn't a slower version of the same particle. It's mathematically inconsistent, a contradiction in the equations, not a difficult engineering problem waiting for someone clever enough to solve it. It's worth clarifying one common point of confusion here, because it comes up often, and getting it right matters. Light does slow down when it passes through a physical medium like glass or water, which is exactly why light bends when it enters a swimming pool at an angle, an effect called refraction that anyone who's ever looked at a straw sitting in a glass of water has actually seen with their own eyes, the straw appearing to bend or break right at the water's surface, purely because light traveling from the submerged portion of the straw to your eye bends slightly as it crosses from water into air. Rainbows work through this exact same underlying principle, sunlight bending by different amounts depending on its color as it passes through raindrops, splitting a single beam of white light into the full visible spectrum arranged in its familiar arc across the sky. But this slowing down isn't the individual photons themselves traveling slower between collisions. It's a more subtle effect involving the photons being absorbed and re-emitted, or more precisely, interacting with the electrons in the material in a way that produces a delay in the overall wave's progress through the medium, while each individual photon in the brief moments between those interactions is still moving at the one true, unchanging speed of light through the empty space between atoms. The speed limit itself never bends. What bends is how directly a beam of light gets to travel that speed without obstruction, weaving through a dense thicket of interacting atoms rather than sailing through open, empty space. Now, here's the detail that made physicists in the early 20th century genuinely uncomfortable when it was first confirmed experimentally. And it's the exact detail that's going to lead us, eventually, to the answer about a photon's age. Light speed in a vacuum isn't just fast. It's the same, exactly the same, for every single observer, regardless of how that observer is moving. If you're standing still and I fly past you in a rocket at 90% of the speed of light, and we both, at that exact moment, measure the speed of a beam of light passing by, we don't get different answers. The way ordinary intuition about relative motion would absolutely demand. If I throw a ball forward from inside a moving train, someone standing on the platform measures that ball moving faster than someone sitting next to me on the train does, because my own motion adds to the ball's speed from the platform observer's point of view. This is such a deeply intuitive fact about the world that we never even think to question it. Ordinary velocities simply add together, straightforwardly, the way you'd expect. Whenever one thing is moving relative to another thing that's itself moving. It's the same logic behind why a plane's speed over the ground changes depending on whether it's flying with or against the wind. And why a person walking forward on a moving walkway at an airport covers ground faster than someone standing still on that same walkway. Light refuses to play by that same perfectly reasonable, perfectly intuitive rule. No matter how fast you're moving, no matter which direction, light measured in a vacuum always comes out to the exact same speed, roughly 186,282 miles per second, or about 299,792 kilometers per second. A number so precisely and repeatedly confirmed that it's now used to define the length of a meter itself, rather than the other way around. A meter, today, is officially defined as the distance light travels in a vacuum during a specific tiny fraction of a second. A definition that only makes sense, that only stays consistent and reliable, precisely because light speed genuinely is the same fixed constant everywhere, for everyone, under every circumstance anyone has ever managed to test. This constancy of light speed isn't a strange, isolated fact that physicists just decided to accept and move on from. It was actually confirmed experimentally before Einstein ever built the theory explaining why it had to be true. In the late 1880s, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily precise instrument specifically designed to detect tiny differences in the speed of light depending on the direction it traveled relative to Earth's motion through space. Their apparatus, called an interferometer, worked by splitting a single beam of light into two perpendicular paths, bouncing each off mirrors and then recombining them, looking for a specific pattern of interference that would reveal even an extraordinarily tiny difference in how long light took to travel each path. It was, for its time, one of the most sensitive measuring devices ever constructed, capable of detecting a difference in light's travel time smaller than anyone had previously been able to measure. At the time, physicists assumed space was filled with an invisible medium called the luminiferous ether, through which light waves propagated the way sound waves propagate through air, and they expected Earth's motion through that ether to create a detectable difference, a kind of headwind and tailwind effect on light's measured speed depending on which direction you measured it. The same way sound traveling with the wind reaches you faster than sound traveling against it. Michelson and Morley's experiment was sensitive enough to detect an effect far smaller than what should have been there if the ether existed the way physicists expected. It found nothing. No difference at all, in any direction, at any time of year, despite Earth's own motion around the Sun constantly changing which direction it was moving through space. The result was so unexpected and so difficult to explain within the physics of the time that it's often described as one of the most influential null results in the entire history of science. A negative finding that ended up demolishing an entire framework physicists had confidently built their understanding of light around for decades. Physicists spent nearly 2 decades proposing increasingly elaborate patches to try to save the ether theory. Contractions of matter in the direction of motion, drag effects where the ether got dragged along with moving objects, none of which held together particularly well once tested further. Each patch requiring another patch to explain away some new inconsistency. It's a genuinely instructive episode in the history of science, watching an entire community of serious, capable researchers try, in good faith, to preserve a framework that was quietly being undermined by their own best experimental evidence, patch after patch. Before someone finally arrived willing to question the framework itself rather than the specific patches needed to save it. It took nearly 2 decades and a young patent clerk working largely outside the mainstream physics establishment to actually make sense of what Michelson and Morley had found. Albert Einstein, at the time working at the Swiss Patent Office in Bern, evaluating other people's invention applications for a living rather than holding any prestigious academic position, spent his evenings and any spare moments he could find working through the deepest puzzles in physics almost entirely on his own, without the resources or institutional support that established professors of the era typically had access to. In 1905, a year so productive for him that historians of science now refer to it as his miracle year. He published several groundbreaking papers in rapid succession. One on the photoelectric effect we just discussed, one providing some of the first solid evidence for the existence of atoms, and one of which was his theory of special relativity. Any single one of which would have been considered a career-defining achievement for most physicists. All three arriving within the span of a few months from someone still working a full-time job entirely unrelated to academic research. Instead of trying to explain away the strange null result, he took it completely seriously, as a genuine, fundamental fact about the universe rather than a puzzle waiting for a clever loophole. He proposed that the speed of light in a vacuum truly is constant for every observer, no matter how they're moving, and then worked out with total mathematical rigor everything that had to be true about space and time themselves in order for that single strange fact to hold up consistently. What he found was that space and time couldn't be the separate, fixed, universal backdrop everyone had always assumed they were. They had to bend, stretch, and adjust differently for different observers moving at different speeds, specifically in whatever way was required to keep light speed constant for absolutely everyone. Time itself, it turned out, was one of the things that had to give. This is where we finally arrive at the piece of the puzzle that's going to let us actually answer tonight's opening question properly. So let's build it up carefully, the same way Einstein himself had to, one logical step at a time. Special relativity predicts something called time dilation. The idea that clocks moving relative to each other tick at different rates, with a moving clock, from the perspective of someone who considers themselves stationary, appearing to run slow. This isn't some kind of illusion or trick of measurement. It's been confirmed directly, repeatedly, using real atomic clocks. In a famous 1971 experiment, physicists Joseph Hafele and Richard Keating flew extremely precise atomic clocks around the world on commercial airliners, in both directions, eastward and westward, and compared them afterward to identical clocks that had stayed on the ground at the United States Naval Observatory. It's a wonderfully down-to-earth way to test one of the strangest predictions in modern physics. 4 cesium atomic clocks strapped into their own seats on ordinary commercial flights. Ticketed passengers alongside them, quietly carrying out one of the most conceptually profound experiments of the 20th century in the cargo hold and cabin of scheduled airline routes. It's genuinely worth picturing the scene, oblivious fellow passengers boarding the same flights, checking their bags, settling into their seats for an ordinary transatlantic or round-the-world trip, with almost none of them aware that a few rows away or a few feet below in the cargo hold sat instruments precise enough to detect a prediction Einstein had made more than 6 decades earlier. One about the very fabric of time itself bending subtly around them as the plane climbed to cruising altitude and picked up speed. The traveling clocks showed a measurably different elapsed time than the stationary ones, differing by an amount, mere nanoseconds, but a real, measured, physically confirmed amount that matched Einstein's predictions with remarkable precision. Once the effects of both their speed and the change in gravitational strength at cruising altitude were properly accounted for. Time dilation isn't a hypothetical. It's a routinely measured, thoroughly confirmed feature of how our universe actually works. One that modern GPS satellites have to correct for constantly since their onboard clocks. Moving at high speed and sitting in a weaker gravitational field than clocks on Earth's surface tick at a subtly different rate than ground-based clocks. A difference that, left uncorrected, would cause GPS location errors piling up by several miles every single day. Every time your phone tells you exactly where you are, it's relying, quietly and invisibly, on engineers having correctly accounted for Einstein's relativity, a genuinely strange thing to realize the next time you use a mapping app to find the nearest coffee shop. Here's the exact mathematical relationship at the heart of time dilation, and I want to walk through it carefully. Because the shape of this equation is what's actually going to answer tonight's question, not just gesture vaguely toward an answer. The amount of time dilation an object experiences depends on its speed relative to an observer, following a specific formula involving what's called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who had actually worked out much of this same mathematics before Einstein, though without fully grasping its true physical meaning the way Einstein eventually would. Lorentz, along with a handful of other physicists working in that same period, had been trying to patch up the ether theory using exactly this same mathematical structure, treating it as a strange but ultimately mechanical correction needed to explain the Michelson-Morley result. Without ever taking the radical leap Einstein eventually did, that this mathematics was describing the true, literal nature of space and time itself, rather than some peculiar physical distortion happening to objects moving through an underlying ether. This factor starts at 1, meaning no time dilation at all for anything moving slowly compared to light, and grows larger and larger, meaning more and more severe time dilation, as an object's speed gets closer and closer to the speed of light. At everyday speeds, the speeds of cars, aeroplanes, even the fastest spacecraft humans have ever built, this factor is so close to 1 that the resulting time dilation is genuinely negligible. A difference of nanoseconds over a flight lasting hours. Exactly the tiny effect Haffel and Keating had to build extraordinarily precise instruments just to detect it all. If you drove a car continuously for an entire year at highway speed, the amount of time dilation you'd accumulate relative to someone standing still would amount to a difference far smaller than the blink of an eye. A difference so tiny it would take incredibly sensitive laboratory equipment, not just an ordinary wristwatch, to ever notice it at all. But watch what happens to that factor as speed climbs higher, closer and closer to light speed. At 50% of light speed, time dilation is already a modest but clearly noticeable effect, a moving clock ticking at around 87% the rate of a stationary one. At 90% of light speed, a moving clock ticks at less than half the rate of a stationary one. From the stationary observer's perspective, meaning a year passing for the traveler corresponds to more than 2 years passing for everyone they left behind. At 99% of light speed, the effect becomes dramatic. A moving clock crawling forward at only about a seventh the rate of a stationary clock, meaning a single year experienced by the traveler corresponds to roughly 7 years passing everywhere else. At 99.99%, dramatically more severe still, the ratio climbing into the dozens, then the hundreds. Every additional fraction of a percent closer to light speed buying an increasingly enormous multiplier on how slowly the traveler's own clock appears to tick relative to everyone who stayed behind. And as speed approaches the speed of light itself, getting closer and closer without quite reaching it, this factor doesn't just keep growing. It grows without any limit at all, approaching infinity, meaning the amount of time dilation experienced approaches being total and complete. A moving clock, in this limit, ticking forward by an amount that approaches zero, no matter how much time passes for anyone watching from outside. Picture a graph of this relationship, speed along the bottom, the multiplying factor climbing up the side. Starting out nearly flat for most of the graph, barely rising above 1 until you get shockingly close to the very right-hand edge, and then in just the last sliver of that graph, the curve shoots almost straight upward, climbing toward infinity in a space so narrow it barely looks like it belongs on the same chart as everything else. If you tried to actually draw that final upward surge to scale on ordinary graph paper, you'd need a piece of paper stretching well beyond the room you're sitting in, just to capture how dramatically that curve behaves in the tiny remaining sliver of speed between 99.999% of light speed and light speed itself. Now, here's the question this naturally raises, the one that gets us right to the edge of tonight's actual answer. If a clock's own experience time keeps shrinking toward zero as its speed keeps climbing toward light speed, what happens at light speed itself? What happens for the one kind of object in the entire universe that doesn't just approach that speed but actually travels at it? Permanently, unavoidably, as a basic fact of what it is? Your first instinct, having just watched that curve climb toward infinity, might reasonably be to say, well, obviously the answer is zero. Plug light speed into the formula, watch the Lorentz factor blow up to infinity, and the amount of time experienced shrinks down to nothing. Case closed. A photon experiences zero time. That's actually the answer you'll find in a huge number of popular explanations of this exact topic, stated confidently, as though it settles the matter completely. Repeated across countless videos, articles, and casual conversations about relativity. Precisely because it's a short, punchy, quotable sentence that captures something true about the underlying strangeness without requiring anyone to sit through the more careful derivation. And it's not entirely wrong in the sense that it points in the right general direction. But it's not quite right either, and the specific way it's not quite right turns out to be one of the more genuinely fascinating subtleties in all of special relativity. One that most casual explanations skip right past, because the full, careful answer is slightly more work to explain properly than the tidy, quotable version. It's exactly the kind of shortcut that isn't malicious or careless, just understandably taken by people trying to convey a genuinely strange idea within the space of a single sentence. And it's exactly the kind of shortcut this channel exists to slow down and actually unpack properly. This is exactly the question physicists have had to sit with carefully. Because the honest answer turns out to be more subtle and more interesting than simply plugging light speed into the formula and reading off a result of 0, and understanding exactly why requires taking one more careful step into how relativity's mathematics actually works. A step that reveals something genuinely strange about the very language we use to talk about a photon's journey through the universe. Here's the careful, honest answer. The one that actually holds up under scrutiny rather than just sounding satisfying. Physicists use a specific, precise concept called proper time to describe how much time an object actually experiences along its own path through space and time, its own personal, internal clock reading, distinct from how much time an outside observer measures passing. For any object moving slower than light, proper time is a perfectly well-defined quantity, calculable, meaningful. Exactly the number you'd read off a clock physically carried along with that object. But proper time, as a mathematical concept, is built specifically around what's called a time-like path through space-time, the kind of path any object with mass necessarily follows. A photon's path through space-time isn't time-like. It's what physicists call null or light-like. A fundamentally different category of path, one where the specific mathematical quantity that defines proper time doesn't shrink towards 0 the way our intuition suggests. It's simply 0, everywhere along the path, identically, not because time has been dramatically compressed down to nothing, but because the entire concept of proper time, built as it is around time-like paths, was never actually designed to apply to something moving at light speed in the first place. This distinction matters enormously, and it's worth taking slowly, because it's the difference between two very different kinds of claim. One claim says a photon experiences an extremely small amount of time, so small it's effectively 0, in the same way a runner's stride, measured precisely enough, technically covers some tiny amount of distance, even in the smallest fraction of a second. The other, more accurate claim says the question how much time does a photon experience isn't actually a well-formed question at all. In the same way, asking what color is the number 7 isn't a well-formed question, not because the answer is difficult to find, but because the concept of color simply doesn't apply to numbers, and the concept of proper time, in the rigorous mathematical sense physicists use it, simply doesn't apply to something traveling on a null path. Here's another way to feel the difference between these two claims, because it's genuinely easy to blur them together if you're not paying close attention. Imagine someone asks you how tall the number 4 is. You wouldn't say extremely short, nearly 0 inches. You'd say the question doesn't make sense, because height is a property that applies to physical objects, not abstract numbers. Nobody would consider that answer evasive or unsatisfying. It's simply the correct, complete response to a question built on a category error. The claim that a photon experiences basically 0 time quietly smuggles in the assumption that time experienced by a photon is a meaningful quantity in the first place, just an extremely small one. The more careful claim refuses that assumption from the outset, and in doing so, actually respects the mathematics of relativity more faithfully than the popular shorthand does. There's a related, deeply technical reason for this that's worth understanding. Because it's not just a philosophical quibble about semantics. Special relativity describes how measurements made by one observer relate to measurements made by another observer moving at a different speed, using a specific mathematical tool called a Lorentz transformation. This tool works by involving that same Lorentz factor we discussed a moment ago, and here's the crucial detail. That factor is mathematically undefined. not just very large, but genuinely undefined, exactly at the speed of light. You cannot perform a Lorentz transformation to the reference frame of an object moving at light speed, because the mathematics itself breaks down completely at that exact point, refusing to produce any answer at all, rather than producing an answer of zero. There is no valid, mathematically consistent way to describe the universe from a photon's point of view. Because a photon's point of view, in the technical sense of an inertial reference frame, simply does not exist. It's not a frame we haven't figured out how to describe yet. It's not a frame at all. In the same way, there's no valid answer to how many minutes are in the color blue. This is genuinely one of the places in physics where the popular, quotable version of an idea, light doesn't experience time, and the precise, technically correct version, the question of how much time light experiences, doesn't have a well-defined answer. Because no reference frame can be attached to something moving at light speed, point in a similar emotional direction, but say meaningfully different things. The popular version implies a kind of answer exists, just an extreme 1-0. The precise version says the question itself dissolves once you look closely enough at what it would actually require to answer. The same way plenty of intuitive-sounding questions turn out, on close inspection, to be built on an assumption that doesn't actually hold. So where does that actually leave us with tonight's opening question, about that beam of starlight that's been crossing space for over 1 billion years? We now have half of the answer, the relativity half, and it's already a genuinely strange one. There is no meaningful sense in which that beam of light has aged 1 billion years, or any amount of time at all, because the very concept of aging, of proper time elapsing along a path, simply doesn't apply to something traveling that path at the speed of light. But this still leaves an enormous question sitting right underneath everything we've covered so far, one that special relativity alone can't fully answer. If a photon doesn't experience time in any meaningful sense, if there's no valid frame of reference from which to even ask what it's like to be a photon crossing that distance, then what, physically, actually is a photon at the deepest level our best current physics can describe? It's tempting, at this point, to imagine a photon as a tiny, sturdy little object, unaffected by time simply because it's moving too fast for time to catch up with it, the way a fast enough runner might theoretically outrun a slow-moving wave crashing toward them on a beach, staying just ahead of it forever, never actually getting wet. But that image, appealing as it is, turns out to be exactly the kind of intuitive picture we need to set aside if we actually want to understand what a photon is, rather than settling for a comforting but ultimately misleading metaphor. A photon isn't a small object cleverly evading time. It's not winning some kind of race against a force, chasing it down. The entire framework of experiencing time, or not experiencing time, in the sense we mean it for ordinary objects, simply doesn't have anywhere to attach itself to something that never had a valid rest frame to begin with. The runner outrunning the wave picture still assumes there's a runner, existing continuously, making choices, aging in some background sense even while dodging the wave. A photon doesn't fit that mold at all, and figuring out what mold it actually does fit requires leaving special relativity's picture of objects moving through space-time behind, and picking up the very different picture quantum field theory offers instead. Special relativity tells us how a photon must move, and why the question of its aging breaks down the way it does. It doesn't, on its own, tell us what a photon fundamentally is, underneath the label, underneath the equations describing its motion. For that, we have to go one level deeper into the framework physicists actually use today to describe what particles like photons really are. A framework called quantum field theory. And it's there, in that deeper picture, that the full, complete answer to tonight's question finally comes together, along with an answer to a question we haven't even properly asked yet. What happens to that billion-year-old light the very instant it finally reaches your eye, ending a journey that, from the light's own perspective, in whatever limited sense that phrase can even be used, never really had a duration to begin with? There's also the strange matter of what that light actually looked like when it left its source, and how much it's changed, stretched, and reshaped along the way, changes that turn out to be genuinely real and measurable, even for something whose own internal clock, in the only sense that clock could ever meaningfully apply, never ran at all. That's a genuinely strange thing to hold in your head at once. A beam of light that hasn't aged in any meaningful sense, and yet has still undeniably changed, stretched by the expansion of space itself over the course of its billion-year crossing. Its wavelength lengthened, its energy reduced, evidence, plain and measurable, that something happened to it during the journey, even while the very concept of during turns out to be more complicated than it first appears once you actually look closely at what light fundamentally is. Holding both of those facts at once, unaged yet changed, timeless yet measurably different from when it started, is exactly the kind of tension that a careful look at what a photon actually is underneath the labels and the equations is finally able to resolve properly, rather than leaving you stuck with two seemingly contradictory statements sitting side by side. It's a resolution worth working toward carefully, one concept at a time rather than rushing to a tidy, quotable summary before the actual physics has had a chance to earn it. Let's actually build that deeper picture properly, because it's going to reshape something even more basic than the age question. The very idea that a photon is a little object traveling from one place to another at all. Everything we covered about special relativity, the constant speed, the breakdown of proper time, the impossibility of a photon's reference frame, is completely correct as far as it goes, and it genuinely does answer the question of how a photon moves and why the concept of its aging fails to apply. But it still leaves the picture of a photon as some kind of small, discrete traveler largely intact. Just one whose internal clock happens to behave in a genuinely strange way. Quantum field theory asks us to go further, and to question whether that picture of a small, discrete traveler was ever quite right to begin with, even before we get to the question of its age. Modern physics describes light and every other fundamental particle using a framework called quantum field theory, and the central idea behind it is genuinely one of the more mind-bending shifts in how physicists think about reality. Under this framework, what actually exists everywhere, filling every point in space, even the seemingly emptiest vacuum, is a collection of fields. Something closer to a kind of underlying, ever-present tension or potential spread continuously across the universe. One field for each fundamental type of particle. There's an electron field spread through all of space, and every single electron anywhere in the universe is simply a localized excitation of that one underlying field, the reason every electron in existence is completely, perfectly identical to every other electron, indistinguishable in every measurable property, because they're not separate objects at all in the deepest sense, just individual ripples in the exact same underlying field. This detail actually solves a puzzle that troubled physicists for a while. Why are all electrons everywhere in the universe without a single known exception? absolutely identical in mass, charge, and every other measurable property, down to the last decimal place any experiment has ever been able to check. Ordinary manufactured objects, even ones produced to extraordinarily high precision, always carry tiny, measurable differences from one another. But there's no such thing as a slightly different electron, anywhere, ever. And quantum field theory explains exactly why they're not separately manufactured objects being compared to each other at all. They're all simply the same underlying field doing the same fundamental thing in different places. There's a field for each type of quark, a field for each of the other fundamental particles physicists have catalogued, and a field for each force-carrying particle as well. And there's an electromagnetic field, the specific field relevant to tonight's question, also spread continuously through the entire universe, in every direction, at every point, all the time. This isn't a hypothetical or a convenient mathematical fiction dreamed up purely for calculation purposes, either. Even though it's certainly a mathematical framework, quantum field theory, and specifically the version of it describing light and charged particles called quantum electrodynamics, is widely considered one of the most precisely tested theories in the entire history of science, making predictions about certain measurable properties of electrons that match experimental results to an accuracy of better than 1 part in a trillion. A level of agreement between theory and experiment that few other scientific theories in any field have ever come close to matching. Richard Feynman, one of the physicists who helped develop this exact theory and later won a Nobel Prize for that work, famously compared this level of precision to measuring the distance between New York and Los Angeles accurately enough to know the exact width of a single human hair. An almost absurd level of agreement between abstract mathematics and physical reality that quantum electrodynamics achieves routinely. Feynman himself, known for his gift at making genuinely difficult physics accessible to ordinary audiences, often expressed a mixture of pride and bafflement at how well this particular theory performed, describing it, in his own characteristically blunt style, as a theory that made ridiculous, almost embarrassing predictions that nonetheless kept turning out to be exactly right every single time anyone bothered to check. It's genuinely worth sitting with that comparison for a moment, because it's easy to hear extremely precise theory and let the phrase wash past without registering how genuinely remarkable that specific level of agreement actually is. Very few human endeavors of any kind, scientific or otherwise, ever manage predictions that hold up to that degree of scrutiny, and the fact that this specific, strange, field-based picture of reality is the one making those predictions is itself a strong piece of evidence that the picture, however unintuitive it feels, is capturing something genuinely true about how the universe actually works, rather than just being a convenient bookkeeping trick that happens to give the right numbers for unrelated reasons. A photon, in this picture, isn't a tiny ball of something traveling through otherwise empty space between a source and a destination. It's a ripple, a specific, quantized excitation of that electromagnetic field, a bit like a single, precisely defined wave briefly rising up out of an otherwise calm ocean and then settling back down. When you excite that field at one location, say an electron in a distant star dropping to a lower energy level and releasing energy in the process, that excitation doesn't need to physically transport a little object across the intervening distance the way a thrown ball transports a small chunk of matter from one hand to another. The field itself, already present everywhere, from the star all the way to your eye, simply ripples in a specific, quantized way that propagates outward, until it eventually interacts with something else capable of absorbing that specific packet of energy. An electron in one of the light-sensitive cells at the back of your eye, for instance, which absorbs that ripple and, in doing so, triggers the chemical reaction that eventually becomes the sensation of seeing. There's a helpful, if imperfect, analogy here involving a stadium wave, the kind sports fans sometimes perform, standing up and sitting down in sequence around an arena. No single spectator physically travels around the stadium. Each person simply moves up and down in place, briefly, and the pattern, the wave itself, propagates around the entire stadium as a coherent, traveling disturbance, even though every single individual person involved never leaves their own seat. If you filmed that wave from high above and only showed the footage to someone who'd never seen a stadium wave before, they might reasonably describe it as something moving rapidly around the entire arena. And in a certain sense they'd be right, something genuinely does move, a pattern, a coordinated disturbance passing from section to section. But if you asked them to point to the specific object doing the moving, they'd quickly realize there isn't one. Just a very well-organized sequence of local, in-place motions creating the appearance and functional reality of something traveling. The wave is real. It genuinely travels. But it isn't made of any single object being carried from one side of the stadium to the other. It's a pattern of local excitation passing through a medium, the crowd, that was already present, seated, everywhere around that stadium the entire time. A photon, in the quantum field picture, works on a conceptually similar principle, just replacing a stadium crowd with the electromagnetic field spread continuously through all of space, and replacing the up and down motion of standing fans with a precisely quantized ripple of field excitation, one specific enough and stable enough to be captured, measured and treated for nearly every practical purpose, exactly like the small traveling particle our intuition wants it to be. This is worth sitting with, because it changes the entire mental picture we naturally reach for when we picture light traveling. We tend to imagine something like a tiny bullet leaving a source, crossing a gap, and striking a target, the same basic shape as almost every kind of motion we have direct experience with. Quantum field theory replaces that picture with something closer to a disturbance rippling through a medium that was already there the entire time, at every point along the way, rather than a discrete object moving through otherwise empty space. The photon isn't the thing traveling. It's the name we give to a specific quantized pattern of excitation in a field that already fills the entire distance between source and destination before anything even happens. It's worth being honest that this is genuinely one of the harder conceptual pivots in all of modern physics. And even physicists who work with these equations every day sometimes describe struggling to hold both pictures: the everyday particle picture and the underlying field picture, comfortably in mind at the same time. The particle language is useful, and it's not simply wrong, so much as it's a kind of approximation, an extremely good and extremely useful approximation for most practical purposes that starts to mislead you the moment you push it into questions like the one we're asking tonight. Questions about what a photon fundamentally is when nobody's measuring it, rather than questions about what a detector will register once a measurement actually happens. There's a specific, important distinction physicists draw here worth understanding, because it directly touches tonight's question between what are called real photons and virtual photons. A real photon is exactly the kind of light we've been discussing all along. An actual, detectable packet of energy that carries momentum, obeys the specific relationship between energy and frequency we covered earlier. and can, in principle, be captured by a detector, whether that detector is a telescope, a solar panel, or the light-sensitive cells inside your own eye. A virtual photon is something considerably stranger, a kind of mathematical bookkeeping device physicists use to describe how the electromagnetic force actually gets transmitted between charged particles in the first place. When two electrons repel each other, quantum field theory describes this interaction as an exchange of virtual photons passing between them. Brief, fleeting excitations of the electromagnetic field that never actually become detectable, real light, and that don't need to obey the same strict energy-frequency relationship real photons do. Borrowing energy briefly in a way ordinary conservation laws would seem to forbid, if not for the extraordinarily short timescales involved keeping everything mathematically consistent. Physicists sometimes describe this using something called the uncertainty principle, a genuinely deep feature of quantum mechanics stating that energy and time can't both be pinned down with perfect precision simultaneously, meaning a brief enough exchange can borrow an amount of energy that would otherwise seem to violate conservation, provided the exchange happens quickly enough, and pays that energy back before anyone could ever catch the books, not balancing. It's a strange kind of cosmic accounting, one where a debt is permitted as long as it's settled fast enough that nobody in principle could ever measure the discrepancy. A rule built directly into the fundamental structure of quantum mechanics rather than some clever loophole physicists invented after the fact to patch over an inconvenient result. This same uncertainty principle, in a different context, is also responsible for why perfectly empty space isn't actually perfectly empty at all, constantly fizzing with these same kinds of brief, borrowed energy fluctuations. Particles and antiparticles popping briefly into and out of existence everywhere all the time, even in a region of space with no matter, no light, and no detectable energy present in any ordinary sense. Virtual photons are never directly detected, precisely because they're not the finished, on-shell excitations that real, observable light consists of. They're closer to an accounting tool within the deeper mathematics, representing the mechanism of a force being transmitted rather than an actual particle traveling anywhere in the ordinary sense at all. Physicists sometimes describe the entire electromagnetic force itself, the reason magnets attract or repel, the reason your hand doesn't pass straight through a solid table, as ultimately arising from this constant, invisible exchange of virtual photons happening between charged particles, an entire fundamental force of nature built at its deepest mathematical level on a kind of particle that can never itself be caught and observed directly. This distinction matters for tonight's question, because it's another reminder that the picture of a photon traveling from here to there is itself a simplified, classical flavored description layered on top of a much stranger underlying reality. One where the language of travel, duration, and distance covered doesn't map cleanly onto what's actually happening in the deepest mathematical description physicists currently have. Here's another detail about photons that reinforces just how different they are from the small, solid objects our intuition wants to compare them to. As far as every experiment ever conducted has been able to determine, a photon has no internal structure and no measurable size whatsoever. It isn't made of smaller components. It doesn't have a surface, a shape, or physical dimensions in the way a marble or even an individual atom does. Physicists have tested this using extraordinarily high-energy particle collisions, essentially trying to probe whether a photon has any kind of internal architecture that might reveal itself under sufficiently violent scrutiny. The same basic strategy that revealed protons and neutrons are themselves built from smaller quarks decades ago. That earlier discovery, back in the late 1960s, came from firing high-energy electrons at protons and finding that the way those electrons scattered wasn't consistent with hitting a smooth, structureless target, but instead revealed hard, point-like components buried inside. The first direct evidence that protons weren't fundamental at all, but were themselves built from smaller pieces. This kind of experiment, called deep inelastic scattering, works on a principle you can actually picture intuitively. Throw something at a target hard enough and precisely enough, and the pattern of what bounces back and at what angles tells you an enormous amount about whether that target is smooth all the way through or has hard, discrete lumps buried somewhere inside it. The same basic logic Ernest Rutherford used decades earlier to discover that atoms themselves have a small, dense nucleus rather than being uniformly spread out clouds of charge. Physicists ran comparable experiments on photons, probing them with the highest energies and most sensitive detectors available, specifically looking for any hint of similar internal structure. Every single test on photons has come back completely negative, consistent with treating the photon as what physicists call a point particle. An object with genuinely zero physical size, not just something too small to currently measure, but something that, according to our best current theories, simply doesn't possess spatial extent as a fundamental property at all. Current experimental limits place any possible photon size at less than roughly a billionth of a meter, a number small enough that it's functionally indistinguishable from true zero given the precision of any instrument ever built. And every theoretical framework describing photons treats that size as being genuinely exactly zero, not merely too small to have been detected yet. To put that number in some kind of perspective, that limit is smaller than the size physicists currently attribute to an individual quark, itself already thought to be a fundamental, structureless point particle with no further internal parts, meaning a photon, as far as any experiment has ever managed to probe, sits comfortably within the same category of genuinely, completely structureless objects, rather than being some intermediate case that merely hasn't been examined closely enough yet. Think about how strange that actually is, compared to literally every object you've ever directly interacted with in your life. Every single physical thing you've ever touched, seen, or held has some size, some boundary separating it from the space around it, however small. Even the smallest dust particle floating in a sunbeam, even a single bacterium invisible to the naked eye, has genuine spatial extent, a measurable width, a definite boundary between itself and the surrounding air. A photon, as far as physics can currently tell, has none of that. It's not a tiny thing. It's not a thing with spatial extent at all, in the ordinary sense that word implies. Combine that with everything we established in the first half of tonight's story. No rest mass, forced motion at light speed, an undefined rather than merely tiny experienced duration, and you start to realize that almost none of the ordinary vocabulary we use to describe objects' size, duration, journey was ever really built with something like a photon in mind. We're using words evolved to describe rocks, animals, and rivers, forcing them onto something that behaves according to an entirely different set of rules, and it's honestly a small miracle that plain language manages to convey as much of the correct picture as it does. even while quietly smuggling in assumptions that don't actually hold. Every single one of our everyday words for physical objects, thing, particle, traveler, journey, carries centuries of accumulated assumptions baked in from a lifetime spent around objects with size, mass, and continuous existence through time. Assumptions so deep we rarely even notice we're making them until something like a photon comes along and quietly breaks every single one at once. Now let's finally close the loop on the tension we ended on a moment ago. The one about that beam of starlight being simultaneously unaged and yet undeniably changed over its billion-year crossing. Because resolving it properly is where tonight's whole story comes together. The specific change happening to that ancient starlight is called cosmological redshift, and it's worth being precise about what it actually is, because it's often confused with a different related phenomenon called Doppler shift. And the distinction matters for understanding exactly what's happening to a photon during its journey. Doppler shift is the everyday phenomenon behind why an ambulance siren sounds higher-pitched as it approaches you and lower-pitched as it speeds away, sound waves getting compressed or stretched, because the source itself is physically moving relative to you, moving through a fixed, unchanging medium of air that isn't itself expanding or contracting. You've almost certainly experienced this directly, standing on a sidewalk as an ambulance rushes past, the pitch of its siren audibly dropping the instant it passes you and starts moving away rather than toward you. A genuinely ordinary, everyday phenomenon that has nothing to do with cosmology at all. The exact same underlying physics explains why a race car sounds like it's dropping in pitch as it roars past a stationary camera at a racetrack, or why a train whistle seems to bend downward in pitch the instant the train passes the platform. Ordinary, familiar sound, doing something our ears learn to recognize instinctively long before anyone ever explains the physics behind it. Cosmological redshift is something different, and in some ways stranger. As light travels across the genuinely vast distances between distant galaxies and our telescopes, the space itself that the light is traveling through is expanding. A real, measured, ongoing feature of our universe first discovered by the astronomer Edwin Hubble in the late 1920s, when he found that distant galaxies appear to be moving away from us and from each other at a rate proportional to their distance, evidence of the universe's overall expansion rather than any single galaxy simply moving through fixed, unchanging space. Hubble's original observations, made using what was then the largest telescope in the world at Mount Wilson Observatory in California, showed a clear, consistent pattern across dozens of distant galaxies. The farther away a galaxy was, the faster it appeared to be receding from us. A relationship now known as Hubble's law, and one of the most important observational discoveries in the entire history of cosmology. Before Hubble's work, most astronomers, including Einstein himself for a time, generally assumed the universe was static and unchanging on the largest scales, neither expanding nor contracting. An assumption so deeply held that Einstein reportedly added an extra term to his own equations of general relativity specifically to force his mathematics to describe a static universe, a modification he later called his biggest blunder once Hubble's observations made clear the universe was doing something his original unmodified equations had actually predicted all along, expanding, just as the mathematics, left alone, had suggested from the start. It's a genuinely humbling historical footnote. One of the greatest scientific minds of the century second guessing his own equations because the resulting picture of an expanding universe felt too strange, too radical to accept at face value, only to watch observational astronomy confirm within just over a decade that his original instinct had actually been the correct one all along. As space itself stretches during light's journey, the light's own wavelength stretches right along with it, exactly the way a wave drawn on the surface of a balloon would stretch out as you slowly inflated that balloon, becoming longer and lower in energy the longer that light spends traveling through continuously expanding space. Picture drawing a simple wavy line on a partially inflated balloon, then slowly blowing more air into it. The wave doesn't move across the balloon's surface in any ordinary sense. It simply gets stretched out longer and flatter as the rubber underneath it expands, the exact same wave just drawn out over more surface area than it originally occupied. Light traveling through expanding space behaves in a conceptually similar way, its wavelength gradually lengthening not because the light itself is doing anything differently, but because the very fabric it's embedded in keeps stretching underneath it as it travels. This is why the most ancient light we can detect, the cosmic microwave background, the faint ancient afterglow left over from roughly 380,000 years after the Big Bang, arrives at our telescopes today not as the visible or infrared light it was originally emitted as, but stretched dramatically into microwave wavelengths. Its original wavelength lengthened by a factor of over 1,000 times over the course of its nearly 14 billion year crossing, direct, measurable evidence of just how much the universe has expanded during the time that light spent in transit. When this light was first released, the universe had cooled down just enough, after its earliest, hottest phase, for electrons and protons to finally combine into stable, neutral hydrogen atoms for the first time, an event cosmologists call recombination, which suddenly allowed light to travel freely through space for the first time in the universe's history, rather than being constantly scattered by a dense, opaque soup of charged particles. Before that moment, the universe was filled with a hot, ionized plasma, electrons and protons flying around independently rather than bound together into atoms, and any photon trying to travel through that plasma would be almost instantly scattered by a nearby free electron, bouncing from particle to particle so constantly that light couldn't travel in a straight line for any meaningful distance at all, the same basic reason you can't see through a thick fog even though the water droplets making it up are individually transparent. If you could somehow have stood inside the universe during that early era, holding a flashlight, the light from that flashlight wouldn't have traveled more than an extremely short distance before being scattered off in some random new direction by the nearest free electron, meaning the entire universe for its first few 100,000 years was genuinely, thoroughly opaque, glowing brightly everywhere but impossible to actually see through in any meaningful sense. The cosmic equivalent of standing inside a dense, luminous cloud with no clear line of sight in any direction at all. The moment recombination happened, that fog lifted essentially all at once across the entire universe, and the light already present at that moment was suddenly free to travel in a straight line, uninterrupted for the very first time. Light that's still traveling, still uninterrupted, reaching our telescopes today as the cosmic microwave background. A genuine snapshot of what the universe looked like at the exact moment it first became transparent to light. That light has been traveling uninterrupted ever since, and its dramatic redshift is one of the strongest, most direct pieces of observational evidence we have for the Big Bang itself, discovered somewhat by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson. who initially thought the persistent background hiss they kept detecting in their antenna was some kind of equipment malfunction, possibly even bird droppings accumulating inside their instrument, before realizing they'd stumbled onto direct, observational proof of the universe's fiery, ancient origin. Penzias and Wilson had actually been trying to use their antenna, originally built for satellite communication research, for entirely different astronomical observations when they first noticed this strange, persistent, uniform static coming from every single direction in the sky with equal intensity, impossible to eliminate no matter how carefully they cleaned their equipment or accounted for every conceivable source of interference they could think of. It took a conversation with theoretical physicists at a nearby university who happened to be independently predicting that exactly this kind of leftover radiation should exist if the Big Bang theory were correct, for Penzias and Wilson to realize what they'd actually found. Neither team had been looking for the other's work. The theorists were calculating what should exist. The radio astronomers had already detected it, sitting in their data for months, mistaken for a persistent, annoying source of noise they couldn't get rid of. A quiet, almost comic footnote sitting underneath one of the most important observational confirmations in the entire history of cosmology. Neither had been designed with the other's existence in mind, and yet together they turned a strange, persistent hiss in a New Jersey antenna into direct physical confirmation that the entire universe really did once begin in an unimaginably hot, dense state, exactly as the theorists working nearby had been calculating all along, entirely unaware that the proof they needed had already been sitting quietly in someone else's data for months. It's the kind of story that reminds you science doesn't always advance through carefully planned experiments chasing a predicted result. Sometimes it advances because two completely unrelated groups of people, working on entirely different problems just a short drive apart, happen to stumble into the same answer from opposite directions, at almost exactly the same time. One side holding the theory, the other holding the evidence, neither realizing until a single phone call that the two halves had been sitting there, complete, waiting only to be introduced to each other, a reminder that even the biggest discoveries sometimes arrive quietly, mistaken at first for nothing more than an inconvenience, waiting patiently to be recognized for what they actually were the whole time, sitting quietly in plain sight until the right two people finally compared notes and realized together exactly what they'd been looking at all along. Quietly, without fanfare, the way most of the universe's biggest secrets actually tend to arrive. It's one of the more charming stories in the history of science, a Nobel Prize eventually awarded not for an experiment carefully designed to confirm a specific theoretical prediction, but for the diligent, careful troubleshooting of what everyone involved initially assumed was simply an annoying equipment problem. Here's the key insight that resolves tonight's apparent tension completely. This stretching, this genuine, measurable, dramatic change happening to light over its journey doesn't require any proper time to have elapsed for the photon itself in order to occur. Redshift isn't something that happens to a photon gradually, moment by moment, the way aging happens to a person gradually, moment by moment, across a lifetime. It's a relationship between two specific events, the event of the light's emission and the event of its eventual absorption, mediated by how much the geometry of space between those two events has changed. It helps to think about this the way general relativity, Einstein's later, even more ambitious theory extending special relativity to include gravity and the overall shape of the universe actually formalizes it. In that framework, a photon's path is described as a null geodesic. Essentially, the straightest possible path something with zero proper time can take through curved, expanding spacetime. And the redshift that path accumulates comes directly out of how the geometry itself changes along that path, not from any internal process unfolding inside the traveling photon. This is the same basic mathematical framework Einstein used to correctly predict how light bends when passing near a massive object like the Sun, an effect famously confirmed during a total solar eclipse in 1919. When astronomers led by the British physicist Arthur Eddington travelled to the island of Principe off the coast of West Africa specifically to photograph stars near the Sun's edge during the brief window of darkness the eclipse provided, measuring starlight bending by almost exactly the amount Einstein's equations predicted as it passed close to the Sun's edge, a result that made international headlines and turned Einstein, almost overnight, into the most famous scientist in the world, his name appearing on front pages of newspapers that had never before devoted serious coverage to a purely theoretical physics result. It's a genuinely remarkable historical moment to picture. A team of astronomers hauling delicate photographic equipment to a remote tropical island specifically to catch a few precious minutes of total darkness in the middle of the day, all in service of testing whether a strange, abstract set of equations, worked out largely on paper by a physicist most of the public had never heard of, actually described how the universe really behaved. The mathematics genuinely doesn't require, and in fact structurally cannot accommodate, an internal experience of duration for the thing doing the travelling, and yet it still produces a completely well-defined, precisely calculable prediction for exactly how much the light's wavelength should have stretched by the time it arrives. A prediction that's been tested and confirmed across an enormous range of astronomical observations, from nearby galaxies whose redshift is small and easily measured, all the way out to the most distant ancient light we can currently detect, where the redshift becomes so extreme it stretches visible light all the way down into wavelengths our own eyes were never built to see at all. The photon's own null path connecting those two events still has zero proper time along it, exactly as we established in the first half of tonight's story. What's changed isn't some internal clock ticking away inside the photon while it experiences the passage of time. What's changed is the relationship between the space-time coordinates of emission and the space-time coordinates of absorption, stretched apart by the expansion of space itself, a change in the geometry connecting those two events rather than a change unfolding through some internal duration belonging to the photon. It's a genuinely useful distinction to hold on to. Change doesn't always require elapsed duration for the thing doing the changing. Redshift is real. It's measured constantly by every telescope studying distant galaxies, and it tells astronomers an enormous amount about the size, age, and expansion history of the universe. But it's a change in the relationship between two events in space-time, not a change unfolding across some internal experience of duration belonging to the photon connecting them. In the same way the distance between two cities can change if the map they're printed on gets stretched, without either city itself needing to experience any kind of internal journey to explain that change. The cities didn't do anything. The space between them changed. Imagine printing a map on a sheet of stretchable rubber, marking two cities on it, and then slowly pulling that rubber sheet outward in every direction. The two cities, as marks on the rubber, don't move independently or travel anywhere relative to the sheet itself. But the distance between them, measured across the sheet, keeps growing, purely because the rubber underneath both of them is stretching. Neither city has to do anything, or experience anything, or undertake any kind of journey for the distance between them to genuinely, measurably increase. So let's finally give tonight's opening question the complete, honest answer it deserves, pulling together everything we've built across both special relativity and quantum field theory. That beam of starlight, having crossed over 1 billion years of cosmic history to reach your eyes tonight, has not aged 1 billion years. It hasn't aged any amount of time at all, because the concept of proper time, of an internal clock ticking forward, requires a time-like path through space-time that a photon, moving at light speed, structurally cannot have. There is no valid reference frame from which to ask what the journey felt like, because a photon has no reference frame at all. A fact built directly into the mathematics of relativity rather than a gap in our current understanding waiting to be filled in by future research. And underneath that relativistic fact sits an even deeper one. From quantum field theory, the very picture of a photon as a small object persisting continuously through a journey, aging or not aging, is itself a simplified, classical-flavored story layered on top of something stranger. A single quantized ripple in a field already present everywhere, connecting one interaction. The light's emission to another, its eventual absorption, without ever needing to be understood as a small, continuously existing traveler in between. Put those two layers together, and the honest, complete picture of what's actually happening when starlight reaches your eye looks less like a marathon runner completing an impossibly long race untouched by time, and more like two distant points in an already existing field becoming connected by a single specific pattern of excitation, a connection that doesn't pass through an interior duration at all, because there was never really an interior traveler there to have one. And yet, despite all of that, the light has genuinely changed. Its wavelength has stretched. Its energy has dropped. Direct, measurable evidence that something real happened during its billion-year crossing. Evidence any astronomer can point a telescope at and confirm directly, spreading that ancient light out through a prism or a spectrograph and reading off exactly how much its wavelength has lengthened compared to what it would have been at the moment of emission. A measurement precise enough that astronomers routinely use it to calculate exactly how far away a given galaxy is and how long its light has been traveling to reach us. That change is completely real. It's just not the kind of change that required any elapsed experience on the part of the photon to bring about, because it's a change in the geometry connecting two events, not a change unfolding through some private internal duration the photon was living through the whole time. Ageless and changed aren't actually a contradiction once you understand exactly what each of those words is doing in this specific context. They were only ever a contradiction under the assumption that change requires duration, and duration requires a valid reference frame, both assumptions that feel completely natural for absolutely everything else we've ever encountered, and neither of which turns out to apply to something moving at the speed of light. It's a genuinely rare thing in physics, or honestly in any field, to find two ideas that feel flatly contradictory on first hearing them, and then discover, after actually doing the careful work of understanding each one properly, that they were never actually in conflict at all. Just sitting on top of two different, easily conflated concepts wearing the same everyday words. I think there's something worth sitting with here that goes beyond the specific physics. Something about what it actually means for you tonight to be looking up at genuinely ancient light. Every single photon reaching your eye from a distant star or galaxy represents a direct, unbroken, physical connection between this exact moment and the exact moment, however long ago, that light left its source. A connection that, from the photon's own structurally undefined perspective, involved no interior gap at all. Think about what that actually means, concretely, the next time you're standing somewhere dark enough to see a genuinely rich, star-filled sky. Some of those points of light left their source before our solar system even finished forming. Others left more recently, but still long enough ago that entire civilizations rose and fell here on Earth during the crossing. Empires built and dissolved, languages invented and forgotten, while a single beam of light kept crossing an empty, mostly featureless distance toward this one particular vantage point on this one particular planet. And yet every single one of those photons, upon finally striking a light-sensitive cell in your eye tonight, is completing, in the only sense that word can meaningfully apply, the exact same kind of connection. A link between two events joined by a path with no interior duration, regardless of whether that path started 10 years ago or 10 billion. There's something worth noticing in the sheer range covered by that single statement, too. The light from the moon left its source roughly 1¼ seconds ago. The light from the sun left roughly 8 minutes ago. The light from the nearest star beyond our own solar system left a bit over 4 years ago. And the light from the most distant galaxies our best telescopes can currently detect left over 13 billion years ago. Nearly the entire age of the universe itself. Every single one of these wildly different timescales, from just over a second to nearly the full age of everything, gets treated identically by the underlying physics, because the photon connecting each pair of events, however far apart in ordinary human terms, experienced exactly the same structurally undefined absence of duration along the way. In a very real sense, tonight's evening sky isn't just showing you old light. It's connecting you, directly and physically, without any intervening duration on the light's own account, to events that happened before Earth existed, before our sun ignited, sometimes before most of the universe's other stars had even formed. That's not a metaphor or a poetic flourish layered on top of the physics for emotional effect. It's the literal, careful, technically accurate consequence of everything we've walked through tonight, and I think it's more genuinely moving than the looser, more popular version of this idea, precisely because it's actually true rather than just poetically true. So here's what I'd like to know, now that we've walked through the complete, careful answer together. Earlier tonight, I asked you to guess how much that billion-year-old starlight had actually aged during its journey. Now that you've heard the full explanation, tell me honestly in the comments, were you closer to the popular, simplified answer? Basically, 0. Or did something about the more careful, technically precise version, the question itself doesn't have a well-defined answer, land differently for you? I'm genuinely curious which version of this idea actually sticks with people once they've heard both. Because in my experience, plenty of people find the more careful, precise answer even more unsettling than the simple one. Precisely because it refuses to give you a tidy number to hold on to at all. There's something almost more comfortable about 0 as an answer, because 0 is still a number, still something you can hold in your head the way you hold any other measurement. Undefined refuses even that small comfort. insisting the question itself was quietly malformed from the moment you first asked it, which tends to sit differently with people than a merely extreme numerical answer does. And if you're the kind of person who wants the full, careful version of ideas like this one, rather than the quick, quotable summary, subscribe. Because that's exactly the kind of explanation this channel is built around. Every single video here starts from a question that sounds like it should have a simple answer, and ends up showing you that the simple answer, however widely repeated, quietly skipped over the most interesting part of the actual physics. Until next time, the next time you look up and catch a genuinely dark, star-filled sky, take a second longer than you normally would. Every point of light up there is a direct physical thread connecting this exact moment to some other moment, sometimes recent, sometimes almost unimaginably ancient. A thread that, from the light's own structurally undefined point of view, has no length at all, and yet still manages, somehow, to carry real information, real change, and a real connection across a gap of time and space large enough to make the whole idea genuinely difficult to hold in your head all at once. Which might be exactly why it's worth trying. There's a specific kind of quiet wonder available in that thought that I don't think requires you to fully resolve every technical detail we covered tonight in order to feel it. You don't need to be able to derive the Lorentz transformation or explain precisely why proper time is undefined rather than merely small, to appreciate the basic shape of what's actually happening every single time you look up at the night sky. You are, quite literally, standing at the receiving end of an unbroken chain of physical connections stretching back across cosmic history, each one completed the instant it began, in whatever sense that phrase can even apply to something that never experienced an interior at all. And every single one of them is real, measured, and confirmed by the same careful physics that gets your GP's coordinates right, that keeps particle accelerators running, and that first predicted, more than a century ago, that light itself would turn out to be far stranger than anyone before Einstein had ever seriously considered. There's something almost more comforting about the more careful, complete answer too, if you sit with it long enough, even though it initially feels less comforting than the simple one. 0 as an answer to how much a photon ages implies a kind of victory over time. A clever loophole a clever enough traveler might exploit. Undefined implies something quieter and, I'd argue, stranger and more honest, that time, duration, and aging were never universal features of reality at all. Just features of one particular kind of path through it, a path most things happen to take, but not the only path available, and not one a photon was ever built to walk. It's worth remembering, too, that none of tonight's strangeness required abandoning careful, rigorous science in favor of vague, feel-good mysticism about the universe. Every single claim we've walked through tonight, the constancy of light speed, the breakdown of proper time at light speed, the field-based picture of what a photon actually is, the mechanism behind cosmological redshift, comes from some of the most carefully tested, most rigorously confirmed physics human beings have ever produced. The wonder available here isn't wonder purchased at the cost of accuracy. It's wonder that only becomes available once you've actually done the careful work of getting the accuracy right in the first place, which is, honestly, the whole reason this channel exists.